This is the final video in the Systems and Proof module for Foundations of Computer Science. The topic is Proving Properties of Automata by Mutual Induction. We're going to prove a very simple property of a very simple discrete finite automaton, which you have seen already. It is the automaton we use to model our on-off switch. Remember, this machine starts in an off state, and every time it receives a push, it moves to another state. So it goes from off to on, and then from on back to off, and around, etc. It does not do anything else. So what we hope to prove is simply that this machine works properly, which is pretty obvious, but we're going to walk through the form of this proof so we can use it in more complicated cases later. So what does it mean for this machine to work properly? Well, one statement we need to show is S sub 1. This is that the automaton is in the state off after n pushes if and only if n is even. That is, if we're in the off state, then we must have received an even number of pushes, and if we have received a number of pushes, then we are in the off state. And that's just checking we're always in the off state when we expect to be. So likewise, we have to prove S sub 2. The automaton is in the on state after n pushes if and only if n is odd. So again, if we're in the on state, that means we received an odd number of pushes, and if we received an odd number of pushes, we are in the on state. Those are all the statements we're going to try to prove, and we're going to use weak mutual induction on the number of pushes. Now, this might seem like a new thing to parameterize on because in our previous examples, when we used n, it referred to a natural number or the derivation height of some element in a post system or the length of a string. And now we're using n to represent some number of pushes. So you might think, where did that come from? But remember, we can always represent our push signal as simply a character in a string. So if we think of our series of push signals as a sequence of characters or a string of characters, what we're really doing is just mutual induction over string length. Now, we have already given a statement of our inductive hypothesis. Our S sub 1 and S sub 2 of n is the inductive hypothesis. However, in this case, it is convenient to break these statements down a little bit further. Namely, because they are biconditional statements, they are if and only if statements, it will be helpful to us to split them into their if and only if portions. This is probably something you know how to do already, but I will just run through it for review. We'll start with our statement S sub 1 of n, and the full statement is the automaton is in the state off after n pushes if and only if n is even. So if we start with the if part of the sentence, that means we start from the end of the sentence and we say if n is even, then it implies the automaton is in the state off after n pushes. That is the if direction. Then to go in the only if direction, we say the automaton is in the state off after n pushes only if n is even. That is the only if direction. To write this a little bit more compactly, just keep in mind that n represents a number of pushes that have been applied to the automaton. So you can think of this as the number of pushes in a string of pushes or the length of that string. Then we can write our two cases simply as the if side, n is even, implies the automaton is off, and the only if side, which is the automaton is off, implies n is even. Next, we just do the same thing for S sub 2. We take the whole statement, which is the automaton is in state on after n pushes, if and only if n is odd, and we start again with the if direction, meaning we start at the back of the sentence, say if n is odd, then the automaton is in state on after n pushes. That is the if direction. And then also we do the only if direction. So the automaton is in state on after n pushes, only if n is odd. And again, we write these both out. N is odd implies the automaton is on, and the automaton is on implies n is odd. So these are our four statements that make up the inductive hypothesis, and we will have to prove all four of them for the base case, and then all four of them again in the inductive step. We begin as usual with the base case, which is just n is equal to 0, meaning we have received 0 pushes so far. And so just plugging 0 into our claim, we come up with the statement that we have to prove if 0 is even, then the automaton is in the state off after 0 pushes. Fortunately, that is definitely true because our automaton starts in the off state, and if it doesn't receive any pushes, it does not go to any other state. So all we have to do is say, since the start state is off, this is true. Now, to prove the only if direction, what we have to prove is that if the automaton is off after 0 pushes, then 0 is an even number. So we start with the antecedent. We assume the automaton is off after 0 pushes. We must show that that means 0 is even. And if you wanted to be extremely thorough, you could write out a definition of even numbers and show that 0 is even. But for this proof, it's not really necessary. We're just going to accept that we all know 0 is an even number, and so this is true. We have now proved the base case for S sub 1, and therefore the next thing to do is to prove it for S sub 2, so that's what we're going to do. When we plug 0 into S sub 2, however, you'll notice that we get kind of a strange statement. We have to prove that if 0 is odd, then the automaton is on. So notice the antecedent of this implication is definitely false. 0 is not odd, and therefore it doesn't really matter whether the automaton is on or not, the implication is true. The terminology we use for this case is we say that it is vacuously true. And an interpretation I would suggest for thinking about what's going on here is we're considering this case that never occurs. We're saying, what if 0 is odd? Well, 0 is never odd, so it just doesn't matter. The statement S2, remember, makes a claim about odd numbers of pushes. If we give it some number of pushes that is not odd, it just doesn't say anything about it. Lastly, going in the only if direction is kind of the same thing, right? We're saying if it turns out the automaton is on after 0 pushes, then we have to show that 0 is odd. But we know that the automaton is not on after 0 pushes because the start state is off. So again, this is false and the implication is true. So we have now proven that our statement S sub 2 holds at the base case where we've received 0 pushes. Since this is vacuous in both directions, sometimes people are tempted to go on and prove also another base case where we check to see whether it holds when we receive 1 push. This doesn't hurt you, but you really don't need to do it because we're doing a weak induction, and that case is covered under our inductive step. Remember, n is greater than or equal to 0, and so when we look at n plus 1, we're really starting at 1 anyway. Okay, so now moving on to our inductive step, we have to show that S sub 1 holds at n plus 1 if S sub 1 and S sub 2 hold at n. And remember, generally S sub 1 is the statement about the relationship between being in the off state and having received an even number of pushes. The exact wording of the phrase we're trying to prove is the automaton is in the state off after n plus 1 pushes if and only if n plus 1 is even. We'll split this up as before into its if and only if parts, starting with if. And what we're trying to show here is just that if n plus 1 is even, we must be in an off state. So we can start out just by saying, let's assume n plus 1 is even. If that is the case, then certainly n is odd. That means then that we can use our inductive hypothesis to conclude that the automaton is in the on state after n pushes. That is what S sub 2 of n tells us. So this is a place where it will be helpful to bring back our diagram and take a look at it. So here it is. This is our state diagram for the automaton. And what we've just established is that we are in the on state after n pushes. So we can reason then that adding one more push will bring us to the off state. And so therefore, after n plus 1 pushes, we'll be in the off state. One way to write that reasoning into the proof is just to refer to the diagram, and we say applying one more push from this state switches from the on state to the off state following the arc labeled push. So therefore, the automaton is in the off state after n plus 1 pushes. So this proves our statement. If n plus 1 is even, then the automaton is off. So now we need to go the other direction. We need to say if we're in the off state, then it is the case that n plus 1 must be even. So we begin by assuming we're in the off state. And we say, if the automaton is in the off state after n plus 1 pushes, we can conclude that it must have been in the on state after n pushes. Again, here we're just referring to the diagram. We're starting with the assumption both that we're in the off state and that we've received n+1 pushes. And then we're working backwards to say, well, we must have been in the on state previously. And we also know that that must have been one push before. So we only had n pushes in the on state. Now, since we're talking about n pushes, we can now again use our inductive hypothesis, and we can conclude that n must be odd. And so therefore, n+1 has to be even. So that's just kind of a preview of what our reasoning is going to be, and now we can write it out. We say by s2 of n, we have that n must be odd, so n+1 is even, and this proves that if the automaton is in the off state after n+1 pushes, n+1 is even. And that completes our proof for s1 of n+1. We now need to go on and finish it for s2 of n+1. Very much like before, we need to show that we can prove our claim s2 at n+1, assuming s1 and s2 hold at n as our inductive hypothesis. Again, just to keep track of what all these variables refer to, s2 is a claim about the relationship between being in the on state and receiving an odd number of pushes. And the exact phrasing is, the automaton is in the state on after n+1 pushes if and only if n+1 is odd. So again, we will split this out and take a look at the if direction first. And what we want to show is that if the number n+1 is odd, then we are in the on state. So we begin with the assumption that the number n+1 is odd. And we can conclude from this, of course, that n is even. And now that we've gone back a step to n, we can use our inductive hypothesis and the statement s1 to conclude the automaton was in the off state after n pushes. So then we take a look at our diagram again, and we use the facts that we've established so far, which are that n is even, and by s1 and the inductive hypothesis, we know that we are in the off state after n pushes. So therefore, it stands to reason that with one more push, we would have n+1 pushes, and we would end up in the on state. So now to add this into our argument, we just say applying one more push from this state switches from the off state to the on state following the arc label push. So the automaton is in the on state after n+1 pushes, and this proves that n+1 is odd, implies the automaton is on. So we've now established s1 in the if direction at n+1. All that remains to do now is show the only if direction, and then we will be finished. So we just need to show if the automaton is in the state on after n+1 pushes, that means n+1 is an odd number. We can start by assuming we're in the on state and we have received n+1 pushes. And again, to get a sense of what's going on, we can bring up the diagram and annotate this to say n+1 pushes corresponds with the on state. And once we've done that, it's pretty clear that the previous state must have been the off state and that we must have required n pushes to get there. But now that we're talking about n pushes, we can use our inductive hypothesis, and we can say by statement s1, if we are in the off state after n pushes, then we know that n must be even. And therefore we can conclude that n+1 must be odd. So we write that into our proof, and we say by s1 of n, we know that n must be even, so therefore n+1 is odd, and that this proves that if the automaton is in the on state after n+1 pushes, then n+1 is odd. And that completes the proof of the only if direction of our statement s2 at n+1, which also completes our inductive step for the statement s2, which completes our entire inductive step for s1 and s2, thereby completing this proof by weak mutual induction and concluding this video, and therefore also concluding the Systems and Proof module for Foundations of Computer Science.